In this video, we're going to look at the integral of log x over 1 plus log x all squared in 3 different ways. Now, I actually already have a video on this channel where we do this integral. This comes from the 2014 Mathematics HSC Extension 2 paper, and it's the very last part of the last question in that exam. So we're going to look at 3 different methods. One of them will be one that I've already done on the channel, but it's nice to compare and contrast different methods. So the first one that I'm going to go through is one that I think most people generally start off with when they try this integral for the first time. So what do we have here? We've got log x over 1 plus log x all squared. And at the moment, it's not really in a form that we can work with. So we can see that there are some functions within functions here. And we know that with integration, one typical technique of integrating is when something's very complicated and you've got functions within functions. Like here we've got a log x within a square function. Something that we typically do is to make a substitution and we let u or t or any letter be the thing on the very inside of our function. So a good idea here might be to say let t equal to log x. So we'll start off with that. On the side, we'll say let t be equal to log x. And you'll see why I'm using t and not the usual letter of u in just a moment. So we've made this substitution. Now we need to differentiate. dt is going to be 1 on x dx. And so if I multiply up, I get x dt equal to dx. And then writing x in terms of t, that's going to give me e to the power t dt equal to dx. Okay, so I can go ahead now and substitute this for dx and this for the log x into my original integral. So my original integral, which I'm just going to call I to save me rewriting it, is going to be the integral of t over 1 plus t all squared times dx, but now dx we're writing that as e to the t dt. Okay, so this is what we have at the moment. And you might look at this and think, well, maybe we could do, if the e to the t wasn't there, if it was just t over 1 plus t squared, that's pretty doable. It's not a very difficult integral in terms of an extension 2 integral. But with this e to the t here, makes things a little bit more difficult. So where do we go from here? Well, what we're going to do is we're going to add 1 and subtract 1 from the numerator. So what's that going to look like? It's going to be the integral of t plus 1 minus 1, and I'll put that in brackets there, over 1 plus t all squared times e to the t dt. Okay, so this, we can now split our fraction into 2 separate fractions. We'll have t plus 1 over 1 plus t all squared minus 1 over 1 plus t all squared, and then all of this gets multiplied by e to the t. And then finally, with that first fraction, I can cancel off a factor of 1 plus t, or t plus 1, and I would get, after doing that and then distributing e to the t, we get e to the t over 1 plus t minus e to the t over 1 plus t, that's a t there, all squared. So this is what we end up simplifying our integral to. This is the point that we get to. Okay, but still these are quite difficult to deal with. This one, not really sure how to integrate that. Same with this, not really sure how to integrate that. And so this is where we're going to have to use some other technique of integration. We're going to have to appeal to integration by parts. So I'm going to actually leave this one here as is. I suppose I probably should write it as 2 separate integrals, just to illustrate what's going on. But I'm going to leave the first one and apply integration by parts to my second one here. So I need to decide, what am I going to choose to be u, what am I going to choose to differentiate, and what am I going to choose to be v dash, the thing that I need to integrate. Okay, so I'm going to choose u as e to the t, and v dash as 1 over 1 plus t all squared. Now the reason that I'm going to choose v dash to be this, you'll see it in just a moment. It's going to be 1 plus t to the negative 2, And when I integrate it, I'm going to add 1 to the power, which is going to make it 1 plus t to the negative 1. And then I divide by this negative 1. And so if I just write that a little bit neater, it'll be minus 1 on 1 plus t. And the reason I'd like this is because this thing looks very similar to what we have in here once we start joining it up with, applying the formula properly and joining it up with the e to the t. I suppose we should differentiate this and get e to the t as well. But anyway, now I can apply integration by parts to this second integral, and you'll see some nice simplifications. So we have the integral of e to the t on 1 plus t dt. That's the first one. That we haven't touched at all. Now we're integrating. It's going to be u times v. So that will be e to the t times minus 1 on 1 plus t minus the integral of u dash times v. So this minus here, part of the v, I'm going to actually bring that outside the integral, and this turns into a plus. Our u dash is e to the t, and our v is 1 over 1 plus t. So this becomes over 1 plus t, like that. Okay, let's see what we've got now. I've got this integral of e to the t over 1 plus t dt, and then when I distribute this minus 1 through to both of these terms, I'll get a minus of that exact same integral. So in fact, this term here is going to cancel with that term there. So I'm just going to cross those out like that. And then what am I left over with? I'm left over with minus this thing. So I've got a minus 1 here and a minus 1 here. That'll give me a positive 1. And so all I'm left over with is going to be e to the t over a 1 plus t. Now this is an integral in terms of t. I should now rewrite it back in terms of my original variable x. E to the t was x, and 1 plus t is going to be 1 plus ln x, log x, plus c. And so this here is my final answer, and that's the first way that we can approach this integral. Okay, now we'll have a look at the second method of approaching this integral, and this method is the one that I've already got on the channel in an earlier video a few years ago. So the trick that we're going to apply now is more of an algebraic trick that you would have to really just be familiar with functions and calculus with certain functions in order to identify this trick. Okay, what are we going to do? Well, here's our integral, and we're going to multiply this integral, or the integrand, the thing being integrated, by a factor of 1. Multiplying it by 1 doesn't change the function, but we're going to write 1 in obviously an interesting way that's going to be beneficial. What we're going to do is we're going to write this integral as x times log x over x times 1 plus log x all squared. Let's use black. 1 plus log x all squared. Okay, why is that helpful? Well, the reason that's helpful is because if you're familiar with the derivative of x log x, you'll know that 1 plus log x appears in that derivative. So I'm now going to apply integration by parts to this, and I'm going to choose u to be x log x, because I want to differentiate that. If I differentiate, that's going to require the product rule. So I'm going to differentiate the first and leave the second. That'll give me log x. And then I'm going to leave the first and differentiate the second. So that'll give me x times 1 on x. And that simplifies to log x plus 1, which you can see is useful because that actually appears in the denominator. So if this is what I'm differentiating, that means I have to integrate everything that's left over. So I'll be integrating 1 over x times 1 plus log x all squared. Now this looks pretty nasty to integrate, except hopefully you can notice, if you're very comfortable and confident with your integrals, that if I was to make a substitution here of, let's say, t equal to log x, the derivative actually sits out the front. The derivative of this log x is 1 over x, which is sitting here. So what I'm going to do is I'm going to write this as 1 on x times 1 plus log x to the negative 2. The benefit of this is that I can see this as some function, f of x, being raised to some power and its derivative sits out the front. So I can apply the reverse chain rule. I don't even have to make some sort of a substitution. I always like to think of these as doing a mental substitution, doing a substitution in your mind. So when we integrate it, it's going to be 1 plus log x. We're going to raise the power of the function and then divide by that power. And now we can apply our integration by parts formula. So this is going to be u times v. U is x log x and v is this guy. So it's going to be x log x multiplied by, if I write this just a little bit neater, I could write it as minus 1 over 1 plus log x. So this becomes, I suppose we can put the minus out the front, and actually we can just write it like this, 1 plus log x minus the integral of u dash times v. Again, we've got that minus 1 factor, which we can include, put it out the front and include there. So that's going to become a plus log x plus 1 over 1 plus log x. And now you see that these things are going to interact, they'll cancel each other out, and we're simply integrating integrating 1, which will give us x. So this is minus x log x over 1 plus log x, plus the integral of 1, which is the x, plus a constant. And now we just want to multiply this up over here, basically make a common denominator, and things will start to tidy up quite nicely. So if I made a common denominator, this would be an x plus x log x. My common denominator would be 1 plus log x plus the constant c. And then you can see that we have x log x minus x log x, which gives us just an x on top, plus c, which matches up with our answer over here, which is a good sign. So that's the second method. Now the final method is not something that you would really need to know for the Extension 2 course, but it is a fun little trick, and one that, you know, when you see certain integrals, you might think about. And you'll see what I mean by that as we do the example. So let's once again just reconsider what our integral is. Our integral, we're integrating here log x over 1 plus log x all squared. Now the thing that I want to notice in this is that in my denominator I have some function, could be anything, but it's all being squared. So this, this is something that's quite interesting, because I think to myself, where else in calculus do we come across functions where the denominator is all squared? And the answer to that is when we look at the quotient rule in differentiation. So just let's remind ourselves of what that is. We have the derivative of some quotient, u over v. And what's that equal to? It's going to be v u dash minus u v dash over v squared. And you can see that our denominator here is going to be some function squared. So this might suggest to us, maybe we can try to rewrite this, the integrand, as the derivative of some quotient. Now we already know, because we've done the question in two different ways, that this integrand here should be the derivative of x on 1 plus log x. So we can already, we already know this. This is information we already know. But if we didn't know that, how do we go about finding this in order to write our integrand as the derivative of x on 1 plus log x? Well, the thing that's being squared has to be the denominator, because that's how the quotient rule works. It's u over v, and then once we do the derivative, it turns out to be a v squared. So what we're going to do is we're going to say, we look for a function, f of x, such that the following is true. The derivative of f of x over 1 plus ln x. So now 1 plus ln x is locked in as the derivative of our quotient, as the denominator of our quotient, but we just have to work out what the numerator is. In hindsight, we already know that it's an x, but we have to work that out. But we want this derivative to be equal to log x over 1 plus log x all squared. Okay, well let's apply the quotient rule to the left-hand side here. if we apply the quotient rule, what do we get? It's going to be v times u dash. So it's going to be 1 plus log x multiplied by the derivative of my numerator minus u times v dash, so minus f of x, times the derivative of my denominator. Now, what's the derivative of 1 plus log x? That's just going to be 1 on x. Not sure why I did that in square brackets. And then all of this is going to be divided by my denominator squared. That's the v squared part. And we know that that needs to be equal to log x over 1 plus log x, all squared. So now our denominators are the same, which means we're just trying to find a function f of x so that the numerators are the same. Okay, so we can basically, what we're doing here is we're multiplying through by the denominator, clearing off the denominators. And so we get 1 plus log x times f dash minus f of x times 1 on x equals log x. Okay, what to do now? Well, at this point, we're going to do a little trick where, you know, when you're doing polynomials and you want to compare coefficients of both sides. We're going to do something similar here, but we're going to compare coefficients of functions. I'm going to compare the coefficient of log x on my left-hand side to the coefficient of log x on my right-hand side. But before I do that, I'm just going to expand everything out. I'm going to get log x times f dash plus an f dash x minus f of x all over x equals log x. Okay, so now I do that comparing of the coefficients. The coefficient of log x on my right-hand side is a 1, and on my left-hand side is an f dash. So what does this mean? This means we need to have f dash x equal to 1, but also we need to have all of this stuff which is left over, which is not a coefficient of log x. What's that got to be equal to? Well, there's nothing else on the right-hand side, so it has to be equal to 0. So this part here has to be equal to 0. So I need this, and I need f dash x minus f of x on x. I need that to be equal to 0. Okay, now this, what's this? This is a differential equation. This is something that you learn in 3-unit maths, and so is this. So let's solve these two differential equations. This one we can solve simply by integrating, and we get f of x equals x plus some constant. Let me just call that constant k. Okay, now in order to find what k is, I have to substitute this thing into this equation and solve for k, and that'll give me whatever value of k I need. Because remember, both of these have to be satisfied. It's not just one of them, both of them have to be satisfied. So we're now going to take this solution, sub it into that equation, that differential equation, and see what value of k pops out. So f dash x, well, if I differentiate this thing, it's a 1. So I get 1 minus x plus k over x is equal to 0. 1 minus x on x minus k on x is 0. 1 minus 1, those two cancel each other off, so I can cross them off. And I'm left with minus k on x equals 0. And so therefore, not x, therefore k is equal to 0. So the value of k which satisfies this differential equation and this differential equation has to be k equal to 0. So this tells me then, therefore, f of x is x plus k, but we just worked out k to be 0, so it's only f of x equal to x. So what does that mean? That means that I can write this function, my integrand, the thing I'm integrating, log x over 1 plus log x all squared, I can write that as f of x, which we just worked out to be x. So I can write this as x over 1 plus log x. So therefore my integral, which is the integral of log x on 1 plus log x all squared, I now rewrite my integrand as the derivative of x over log x. Sorry, not log x, it should be 1 plus log x dx. And then we use the fundamental theorem of calculus. If I'm integrating something that just got differentiated, these two things are basically like inverse functions, and so I'm left over with the integrand, but of course we also just need that plus c on the end as well. So this is going to be x over 1 plus log x plus our integration constant c, and that answer matches the previous two methods as well. So this method here is quite a nice little trick. It would only really be used as a last resort method if you can't think of anything else, and you can notice that the integral, the integrand, the thing being integrated has a square in the denominator. You might like to try this. Sometimes it will get extremely complicated and just not worth doing, but in a scenario like this, it is doable, so it's quite nice. Okay, and that's the end of the video.